Good morning, students. This is Arvind, Asst.Professor DBSIT Kavali. So, in the previous classes, I discussed about some different armature reaction on of an alternator, and now I am going to discuss mainly the phasor diagram of an alternator. So, before going to the phasor diagram of alternator, I am going to discuss some voltage regulation, synchronous reactance, and synchronous impedance of an alternator, and next voltage equation of an alternator, and then coming to the main topic, that is phasor diagram of alternator. Okay, so firstly we will see what is the voltage regulation. So voltage regulation means the change in terminal voltage from no load to full load, and it expressed as a full load terminal voltage. It is called voltage regulation of an alternator. So okay, so the change in terminal voltage from no load to full load, and it is expressed as a full load terminal voltage. It is called voltage regulation of an alternator. So here I am writing this as the equation, that is regular percentage of regulation is equal to E naught minus V by V into 100. Here E naught is the no load voltage and V is the full load voltage. So the difference between no load voltage to full load voltage by full load voltage into 100 is known as percentage of voltage regulation. Okay, next, so the value of regulation not only depends upon load current. So actually the voltage regulation is mainly depend upon load current, but here it is also depend on power factor of the load. So I already discussed these things in the armature reaction, power factor of the load. That in that one I also discussed unity power factor load, next zero power factor, zero lagging power factor, and zero leading power factor loads. So here also the value of regulation is also depends upon power factor of the load. And next, for lagging and unity power factor condition, there is always drop in terminal voltage. Okay, for lagging and unity power factor condition, there is always drop in the terminal voltage. I already discussed I am already discussed these things. That is, we have three types of low power factor loads. One is unity power factor, and another one is lagging power factor, and another one is leading power factor. So here, so for lagging and unity power factor condition, there is always drop in the terminal voltage. Hence, regulation values are positive. Okay, hence regulation values are positive. While for leading power factor, the terminal voltage increases. Hence, regulation is negative. So clearly, it shows that for lagging and unity power factor, the regulation values are positive, and for a leading power factor, the regulation value is negative. Okay. Next, synchronous reactance. So the sum of armature reactance and leakage reactance of an armature is called synchronous reactance. So I already discussed these things in the previous class, like leakage reactance and armature reactance. So these are all the parameters of armature winding. So here the sum of armature reactance and leakage reactance of the armature is called synchronous reactance. So here the synchronous reactance is denoted by the letter X suffix S. Okay, therefore Xs is equal to, I already said that the sum of armature reactance, that is XL, plus leakage reactance of the armature, that is XA, ohms per phase. This is the definition for the synchronous reactance. And next, coming to synchronous impedance. So that is, it is the combination of synchronous reactance and armature resistance is called synchronous impedance. Okay, it is the combination of synchronous reactance and armature resistance is called synchronous impedance, and it also denoted by the letter Z suffix S. So previously we discussed synchronous reactance, that is represented with the letter X suffix S. So here the synchronous impedance is denoted by the letter Z suffix S. So therefore Zs is equal to, we know already, impedance is the combination of resistance and reactance. So here the synchronous reactance is the combination of armature resistance, that is Ra, and synchronous reactance X suffix S, ohms per phase. So here it is the imaginary part. So real part is resistance and imaginary part is reactance. So here Zs is equal to root of Ra square plus Xs square. So this is the synchronous impedance definition and formula. And next, coming to Equivalent circuit of an alternator. This one is also important. It will ask you in the exams also from this chapter. So from the previous discussion, so that means in the armature reaction and in the voltage regulation, and next some topic, that is synchronous reactance and synchronous impedances. So from the previous discussion, it is clear that in all there are three important parameters of armature winding. So I already discussed this topic in the previous class, that is the parameters of armature winding. So that is three important parameters of armature winding, namely armature resistance Ra, leakage reactance XL, and armature reaction reactance XAR. So here, if E phase is induced EMF per phase on no load condition, then on load it changes to E. It changes to E due to armature reaction as shown in the equivalent circuit. So this is the equivalent circuit of an alternator. So here I am taking XAR, this is the armature reaction reactance, and XL is the leakage reactance, and RA is the armature resistance, and it is connected to the E phase, that is the phase voltage at no load. So whenever we connect these parameters into load, we have the terminal voltage Vt, and it consists of armature current Ia or load current IL. So this is the actual equivalent circuit of an alternator. So the equivalent circuit consists of three parameters, that is armature reaction reactance, leakage reactance, and armature resistance, and E phase, that is the phase voltage at no load, and E dash phase, that is the phase voltage at load condition. Okay, and Vt is the terminal voltage. So if E phase is induced EMF per phase at on no load condition, then on load it changes to E dash due to armature reaction. Okay. Next, as current flows through the armature, there are two voltage drops occurs across Ra and XL, that is the armature resistance and leakage reactance. Those are as IARA and respectively. Okay, and next, hence finally terminal voltage Vt is less than E dash by the amount equal to the drop across Ra and XL. So I already discussed it, as current flows through the armature, there are two voltage drops across Ra and XL as IARA and respectively. And next, hence finally terminal voltage Vt is less than E dash by the amount equal to the drops across Ra and XL. So that is, so actually in practice, the leakage reactance XL and the armature reaction reactance XAR are combined to get synchronous reactance. So I already discussed it in the previous slides also. That is the synchronous reactance. That is the combination of XAR plus XL. So in practice, the leakage reactance XL and the armature reaction reactance XAR are combined to get the synchronous reactance XS. So if you see the diagram, so here I am removing the XCR and XL and putting XS, that is the synchronous reactance, in place of leakage reactance and armature reaction reactance XAR. So the diagram changes like this. Okay, hence equivalent circuit of an alternator gets modified as shown in the figure. So if you see this diagram, this is the modified equivalent circuit diagram of alternator. So practice these two diagrams, and they will ask for 2 marks or 5 marks. So we will explain like this equivalent circuit of an alternator. And next, coming to the equation of an equivalent circuit of an alternator. So that is, in the equivalent circuit we have E phase, that is induced EMF per phase on no load, and Vt, that is the terminal voltage per phase on load, and Ia, that is the armature resistance per phase, and Zs, that is the synchronous impedance per phase. So from this equivalent circuit, E phase is equal to Vt plus Ia Zs. This is the phasor sum. Okay, E phase, that is the induced EMF per phase on no load, that is equal to Vt phase, that is the terminal voltage per phase on load, plus Ia Zs. So you know already Zs is equal to Ra plus Jxs. So from this one I am writing Ia Zs, that is the phasor sum. Okay, phasor sum of an alternator. Next, coming to the voltage equation of an alternator. So here I am taking E. So if E is the induced EMF per phase in the alternator, then the following voltage drop occurs in the alternator. That is, the drop across the armature resistance, that is IARA, the drop across the synchronous reactance, that is XS, that is equal to IAXS. After supplying the drops, the remaining voltage is available as the terminal voltage. Okay, after supplying the drops, the remaining voltage is available as the terminal voltage. So from this one I am writing E phase is equal to V phase plus IARA plus IAXS. So here IARA and IAXS is the drops across the armature resistance. Similarly, synchronous reactance. Okay, so this equation is called voltage equation of an alternator. So V phase is the terminal voltage or phase voltage of an alternator on load, and E phase is the voltage induced EMF on no load. Okay, E phase is equal to V phase plus IARA plus IAXS. This is the voltage equation of an alternator. This also they asked for 2 marks. And next, coming to the main topic, that is phasor diagram of an alternator. So from that equation, that is E phase is equal to V phase plus IARA plus IAXS. So from that equation I am taking, we can draw the phasor diagram for various load power factor conditions. So based upon that equation, we will draw phasor diagram for various load, that means power factor conditions, and establish the relationship between E phase and V phase. That is, the E phase is the induced EMF on no load, and V phase is the terminal voltage at load condition, at on load. So in terms of armature current, okay, that is load current and the power factor, that is cos phi. You already know the power factor, that is cos phi. So for drawing the phasor diagram, consider all per phase values and remember following steps. So if you want to draw the phasor diagram of an alternator, so you have to follow some steps. So I will discuss how to draw the phasor diagram. So for that one I am taking steps to draw the phasor diagram. So first one is choose the current as a reference phasor. So actually, if you want to draw the phasor diagram of an alternator at any power factor condition, so we will take current as a reference phasor. And next, coming to the second point, that is second step. Now if load power factor is cos phi, it indicates that angle between V phase and IA is phi. Okay, it indicates that angle between V phase and IA is phi, as V phase is the voltage available to the load. So I already told this one, V phase is the voltage available to the load. Okay, actually here phi is the angle between V phase and IA. Okay, next, so show the phasor V phase in such a way that angle between V phase and IA is phi. So here for lagging power factor, that is cos phi, IA should lag V phase. So IA should lag V phase, and for leading phi, IA should lead V phase. So this is the difference between lagging and leading power factors. So for lagging, the angle between IA and V phase is phi, but here IA should lag V phase, and for leading, IA should lead V phase. Okay, for unity power factor load, phi is 0. The angle between voltage and current is 0. So V phase and IA are in phase. So for lagging power factor, IA should lag V phase, and for leading power factor, IA should lead V phase, and for unity power factor, V phase and IA both are in phase. Okay, and next, coming to the third step. Now the drop IARA is a resistive drop. So I already said that due to the armature reaction in the circuit, the drop across the armature resistance is IARA. So now the drop IARA is a resistive drop, and hence will always be in phase with IA. So this IARA resistive drop is always in phase with IA. So phasor IARA direction will be always same as IA. Okay, that is parallel to IA. But as it is to be added to V phase, IARA phasor must be drawn from the tip of the V phase phasor drawn. Okay, and next, fourth step, the drop IAXS is drop across purely inductive reactance. So in pure inductance, current lags voltage by 90 degrees. Okay, so IAXS phasor direction will be always such that IA will lag IA axis phasor by 90 degrees. So, but this phasor is to be drawn from the tip of the IARA phasor to complete the phasor addition of V phase, IARA and IA axis. Okay. So, and next coming to the fifth one, joining the starting point to the terminating point, we get the phasor E phase. So, next, whatever may be the load power factor, that is either a unity power factor or a lagging power factor or leading power factor, IARA is a resistive drop. So will be in phase with IA. So I already discussed this in the previous slides also with IA. While IA axis is purely inductive. So this is also I discussed. IA axis is purely inductive drop and hence will be perpendicular to IA in such a way that IA will lag IA axis by 90 degrees. Okay, resistive drop means, that means if we take the resistive load, that is the uh, unity power factor. Okay, and next, if we take the purely inductive load, that is lagging power factor, and if we take the capacitor load, that is the leading power factor. So this is shown in the figure. If you observe this diagram, so here, so I already said that the IARA drop is always in phase with IA. So if you see this diagram, the it shows. And next, so if it is a purely inductive drop, so if it is a purely inductive drop, hence will be perpendicular to IA. So if you see this diagram, the perpendicular line gives the, in such a way that IA will lag IA axis. IA will lag IA axis by 90 degrees. That is with respect to IA axis. Okay. So that is this one. And IAZS, that is the uh, total drop IAZS. Okay. And next we have, so firstly we will take lagging power factor load. So the power factor of the load is cos phi lagging. So I already said that. So the power factor of the load is cos phi lagging. So IA lags V phase by angle phi. So if you see this diagram, I am taking current as a phasor. So that's why I am. If you observe this diagram, so I am starting the line from O point. That is the starting point. Okay, so from O to IA, I draw one horizontal line, straight line, that is the current phasor, that is IA. So here I am taking the lagging power factor load, that means here the V phase lags the IA by 5 degrees, phi, angle phi, that is the phase angle. So if you observe this diagram, so the V phase is lags the IA by 90 degrees. So by using steps discussed above, that is those 5 steps, phasor diagram can be drawn as shown in the figure. So I already said that. So the IARA drop is always in phase with IA, that is parallel to IA. So if you observe this diagram, so the IARA drop line is drawn parallel to IA. Okay. Next we have IA axis drop and IA ZS drop. So and finally we have the phasor voltage drop. Phasor voltage, sorry, phasor voltage, not a drop. So E phase, that is the phase EMF, induced EMF in the phase. Okay. So here I am taking IA as a current reference phasor. So based on this IA, so here I am taking lagging power factor. That means the V phase lags the IA by 90 degree, some angle, not exactly 90 degrees. It lags by some angle. So the angle, the difference between the is phi angle. The angle is phi. So here I already said that IARA drop, that is the armature resistance drop, IARA. So the resistive drop is always in the same direction of IA. That means it is always parallel to, it is always drawn parallel to the IA. So it is indicated with the line AB. So O, so if we see, O is the starting point and O to A. So that is O to A is the V phase. That is the phasor voltage or terminal voltage at load condition. So OA is equal to V phase. From this phasor diagram I am writing OA is equal to V phase and AB is equal to IARA. That is the resistive drop. due to the armature reaction. So IARA and BC that is equal to IA excess. This is also one type of drop, and OC that is the E phase, and next AC, so that is the IA-ZS. Okay, these are the points I am taking from this phasor diagram, that to lagging power factor load. Okay, and next, so to derive the relationship between E phase and V phase, the perpendicular are drawn on the current phasor from points A and B. Okay, these intersect current phasor at points D and E respectively. So if you see this diagram, so by using the phasor diagram, we will derive the relationship between E phase and V phase. So here, that's why the perpendiculars are drawn on the current phasor from points A and B, and these intersect current phasors at points D and E. So if you see this diagram, A and B and D and E, so these dotted lines will show the perpendiculars are drawn and intersects also. Okay, AB, DE. Okay, AB and DE, dotted lines. Okay, and next, from this one I am writing E phase whole square is equal to, that is the E phase means you know already, the square of the E phase, that is the induced EMF on no load, that is E phase whole square is equal to OD plus DE whole square plus BE minus BC whole square. So this is the equation from the phasor diagram, that is E phase whole square is equal to OD. So OD means, so this one from O to D, this is in the IA phasor. So in the armature current phasor line, on the current phasor, I am taking OD line. So that is OD and D. So this one D. That means total E phase whole square is equal to OD plus DE. That is total armature current. That is OD plus DE whole square plus BE minus BC whole square. BE minus BC whole square. So BE minus BC, that is the total perpendicular line. BE minus BC whole square. So this is from the Pythagoras theorem. So you already know, it is also familiar. Okay, so from the Pythagoras theorem I am taking E phase whole square is equal to OD plus DE whole square plus BE minus BC whole square. So from this one I am writing E phase whole square is equal to OD is the V phase cos phi. So this line OD. So you already know OA is equal to V phase. Okay, so the angle, that is the power factor cos phi, I am taking from this one, that is V phase cos phi. OD is equal to V phase cos phi. Okay, V phase cos phi plus DE is the IARA, DE. So DE. So IARA also AB, that is equal to DE. Why? Because IARA is always in phase with IA, that is in the direction of IA. That's why I draw the IARA drop parallel to IA. So that is AB, that is equal to DE. So if you see the diagram, the AB is equal to DE points. That's why here DE is also IARA. So AB is equal to DE is equal to IARA. Okay, that's why I am writing V phase cos phi plus IARA whole square plus BE. So BE is the V phase sin phi. So for OD I am taking V phase cos phi, and for BE I am taking V phase sin phi. BE minus BC. Okay, BE minus BC. So BC you already know, that is IA axis. Okay, V phase sin phi minus IA axis whole square. So from this one I am writing squaring on both sides. We have E phase is equal to root of V phase cos phi plus IARA whole square plus V phase sin phi plus IARA IA axis whole square. IA axis whole square. And next, lagging power factor load. So it can be observed that the sign of the y-axis is negative. So if you observe the equation, that is V phase sin phi minus IA-axis whole square, IA-axis, that is So it can be observed that the sign of the y-axis is negative as against its positive sign for lagging power factor load. For lagging power factor load. So this is because Xs consists of XAR, that is the armature reaction reactance. Xs consists of XAR, that is the armature reaction reactance. So armature reaction is demagnetizing for lagging while magnetizing for leading power factor loads. So armature reaction is demagnetizing for lagging while magnetizing for leading power factor loads. You already know in the topic armature reaction I discussed these things. So sign of I-axis is opposite for lagging and leading power factor conditions. Okay, so sign of I-axis is opposite for lagging and leading power factor conditions. And next, coming to the leading power factor load. So here also I am taking IA line as the phasor, reference phasor. So here I am starting from the O point and draw a perpendicular, draw a straight line to IA. So in that line I am taking 3 points, that is one is O, that is the starting point, and DE. So here the V is leading. So the V phase is leading IA, that means with a phase angle phi. Okay, so if you see this diagram you will know. So I already said that the resistive drop IARA is always in the same direction of IA. Okay, in the same direction of IA, that means I am draw IARA drop parallel to IA line. So that's why I am adding that IRA drop to the V phase line. So it is indicated with the points AB. So I am drawing a perpendicular lines to IA phasor line, that is indicated with the letters D and D points. The two perpendicular lines, that means AB is equal to DE, that is equal to IARA. And next I am drawing on perpendicular to the BC. So that is IA axis. Okay, and next I am drawing a dotted line. It intersects the A and C points, that is IAZS. So this is the phasor diagram for leading power factor. And next from the phasor I am taking OA is equal to V. So from this diagram I am taking OA, that is equal to V phase or V. Okay, and next I am taking AB is equal to DE is equal to IARA. So AB is equal to DE is equal to IARA. And next BC is equal to IA axis. So from this diagram BC is equal to IA axis. And next AC is equal to IAZS. So AC, that is equal to IAZS. Okay, and next OC is equal to E naught or E phase. So OC, so this line, this is the E naught. Okay, and next, to derive the relationship between E naught and V, the perpendiculars are drawn from points A and B. These intersect current phasors D and E respectively. That's why I am writing AB is equal to DE is equal to IARA. So from the triangle, that is from the phasor diagram, from the triangle OAD, that is this one. So from the triangle OAD, so this one OAD, so from this one I am writing OAD is equal to, that is from OAD cos phi is equal to, so you already know from the trigonometric functions, you know cos phi is equal to some formula is there. By using that formula, cos phi is equal to OD by OA, that is equal to OD by V. That means OA is equal to V. You already know this one. So that is OA is equal to V. That means OD by V. So from this one I am writing OD is equal to V cos phi. Similarly, sin phi is equal to, from the triangle only, sin phi is equal to AD by OA. So that is equal to AD by V. So from that one also OA is equal to V. You already know that. From this one I am writing AD is equal to V sin phi. So that is equal to B. From that is equal to B. From the Phasor diagram, AD is equal to V sin phi, that is equal to B. So from triangle OCE, so here I am taking another triangle, that is OCE. So this one OCE. So this one I am taking. So from that one I am writing OCE. From the triangle OC square is OC square is equal to CE square plus OE square. From the Pythagoras theorem, OC square is equal to CE square plus OE square. So that is here from the Phasor diagram I am writing CE is equal to BE minus BC. So BE minus BC. Okay. And next, plus OE is OD plus DE. So from the Phasor diagram I am writing OCE triangle, I am writing OE is equal to OD plus DE. OE is equal to OD plus DE. Okay. So from that one I am taking, so BE is equal to, you know, V sin phi. So that is V sin phi minus, you know, BC is equal to IAXS. So V sin phi minus IAXS whole square plus OD is V cos phi plus DE means IARA whole square. So from that one I am writing OC is equal to root of V cos phi plus IARA whole square plus V sin phi minus IAXS whole square. And next, coming to the unity power factor load, the power factor of the load is unity, that is cos phi is equal to 1. So here the phase difference is 0. So phi is equal to 0, which means V phase is in phase with IA. So phasor diagram can be drawn as shown in the figure. So if you see the diagram, phasor diagram, so in this case, actually in the previous loads, that is the lagging power factor and leading power factor, I am taking V phase and IA in one time lagging and one time leading. But here I am taking unity power factor, that means voltage and current both are in phase. So that's why I am taking V phase and IA in the same phase only. So I already said that the current IA is always in direction to the drop IARA. That's why IARA drop is also drawn on the same line. Okay. And next, the IA excess drop is drawn perpendicular to the IA, that is IA is perpendicular to IA axis, that is exactly 90 degrees. And next I am drawing a dotted lines, it intersects the C point from A, that is IAZS, and O to C I am drawing a line, that is E phase. That means OA is equal to, from this phasor diagram I am writing OA is equal to V phase, AC is equal to, what means AC is equal to IAZS, AB is equal to IARA, BC is equal to IAXS, OC is equal to E phase. Okay. And next, consider the triangle OBC, for which we can write, that means OBC, that is OBC. So this diagram, this triangle I am taking. So from that one I am writing OC whole square is equal to OB whole square plus BC whole square. This is from the Pythagoras theorem. You know already OC is equal to E phase. So E phase whole square is equal to OB is OA plus AB whole square plus BC whole square. So E phase whole square is equal to, you know already OA is V phase plus AB is IARA plus BC is IAXS. Substitute these values into this one. We have E phase is equal to root of V phase plus IARA whole square plus IAXS whole square. So as cos phi is equal to 1, so sin phi is equal to 0, hence does not appear in the equation. And next, the phasor diagrams can be drawn by considering voltage V phase as a reference phasor, but to derive the relationship, current phasor selected as a reference phase. So actually if you take V phase as reference phasor also, but to derive the relationship between current phasor, selected as a reference makes the derivation much more simplified. Hence, current is selected as a reference phasor. And it is clear from the phasor diagram that V phase is less than E phase for lagging and unity power factor conditions due to demagnetizing and cross magnetizing effects of armature reaction, while V phase is more than E phase for leading power factor condition due to magnetizing effect of armature reaction. Okay. And next, so thus in general for any power factor condition, E phase whole square is equal to V phase cos phi plus IARA whole square plus V phase sin phi into IAXS whole square. The plus sign is for power factor lagging power factor loads, and minus sign is for leading power factor loads. Okay, and V phase is equal to per phase rated terminal voltage, and IA is equal to per phase full load armature current. And next, coming to the last topic in the unit 1, that is load characteristics of an alternator. So actually the variation of terminal voltage with the load current IL or armature current IA of an alternator is known as load characteristics. Okay, the variation of terminal voltage with the load current IL or armature current IA of an alternator is known as load characteristics. So if the excitation current and speed of the alternator is maintained constant, that is the alternator has constant E0, that is the induced EMF at no load. Okay, then its terminal voltage changes with change in load current or armature current. So under no load, the load current is 0 and hence E0 is equal to V. Okay. And next, so for lagging power factor load, the terminal voltage V will be less than E0. And for unity power factor load, V is more than E0. Okay, so but it is again less than E0 at lagging power factor. Hence, from the above phasors, it can be concluded that the armature terminal voltage V fall on lagging power factor loads, and it can rises on leading power factor loads. Okay. So this is the load characteristics of an alternator. So here I am taking the graph between or the characteristic between load current IL versus V phase terminal voltage. So here I am taking three power factor loads. So leading power factor load, lagging power factor load, and unity power factor load. That E phase line gives the normal voltage. So that is the normal voltage or constant voltage we have. For the leading power factor, it is above E phase, and for unity power factor and lagging power factor, the curve is less than E phase. Okay, this is the load characteristics of an alternator. This will also ask for 5 marks or 2 marks from this chapter. Okay, thank you. In the next class, I will discuss. I am starting the second chapter, that is voltage regulation methods of an alternator. Okay, thank you.